This is video 22 in our series on tensor calculus. In this video, we're going to build on what we've learned about contraction and develop a technique known as raising and lowering indexes. Back in video 17, we used this expression to define our contravariant metric tensor as the matrix inverse of the covariant metric tensor. The matrix product of these two will yield the Kronecker delta or the identity matrix. We then went on to use this expression to define the contravariant basis vector. And by looking back at the last video, you'll recognize this now as an inner product or a contraction between the covariant basis vector and the contravariant metric tensor. Okay, I want to continue along with some analysis here. I want to form a contraction or an inner product with the covariant metric tensor. So I'll do it this way. And I need a new letter, M, and ZMI times ZI like this. I've simply multiplied this factor times the left side. And of course I have to do the same on the right. ZMI times ZIJ ZJ like this. So I have altered the meaning of the I index from a free index to a dummy index and introduced a new free index of M. On the right-hand side, we have a double contraction. All right, now you'll recognize, I hope, that this expression is the same form as this. And that means that our product of terms there really will result in a Kronecker delta Jm. That times Zj like this. And now the Kronecker delta absorbs the J index, leaving us with just Cm. Okay, and finally I want to swap sides of the equation. I want this on the left and this on the right. And I want to rename some indexes. I'd prefer this to be I, so I'll rename it here and here. And to do that, I have to rename I to something else like J. That's what I'll do. So the final expression I'm looking for would be Zi, that's this guy over here, equals Zij times Zj, just like this. Now if you look, you can see that we have an expression here that is like the mirror image of what we started with. It's the same form, it's just that the indexes are in the opposite position. Here we started with the covariant basis vector times the contravariant metric tensor, and we got the contravariant basis vector. Here it's just the opposite. We start with the contravariant basis vector times the covariant metric tensor, and we get the covariant basis vector. So these two are actually inverse operations of each other. We start with the basis vector that has the lower index here, go through the operation, and we wind up with the basis vector that has the upper index. Here we start with an upper index, and it yields a lower index there. So we call this kind of operation, we refer to it as raising the index. We raise the J index here up to I, and here this is an operation of lowering the index. We started with an upper index, and we're able to determine the lower index as a result. Okay, let's keep going. We know that a vector, any vector, can be represented as a linear combination, and we can do it in two ways. We can use the contravariant component times the covariant basis vector, or the covariant component times the contravariant basis vector. Either one works. Well, now that I have this kind of relationship where I can go back and forth, I can now replace the contravariant basis vector here with the equivalent expression which we just derived, which was, well, actually it's part of the definition up here. So I'm going to replace it this way. So I hope you see what I've done. I have taken this expression and replaced it with this expression over here, like so. Okay, and when I do that, I'm now going to do some index renaming. I'm going to rename I to J and J to I. So we'd have VJ, ZJI, ZI like this. And I'm going to reorder some terms. We'll put the metric tensor in front, but I can also switch the index order because this is a symmetric matrix, symmetric tensor. So that ZJI is the same as ZIJ. I'll put our scalar component next and the basis vector at the end. Now at first it looks like I'm just doing operations at random, but not really here because I've now manipulated it so this factor is the same as this one, which means that this scalar component out front must be exactly equal to this expression right here. So I now can say that Vi, our scalar component, is equal to this expression, which is Zij Vj, like so. And if you look closely, you can see that the form of this expression is exactly the same as the form of this expression right up here. So again, we have a situation where we start with a lower index here, use the contravariant metric tensor as a factor to form a contraction or inner product, and it yields the counterpart of the component that has the upper index. We have raised this index. All right, now it shouldn't be much of a stretch of the imagination to see that if you start with this guy and go through this set of operations, it yields this. Well, it's not a stretch of the imagination to realize that if we start with this one, do the same kind of operation, then you're going to come out with Vi, lower index, equals Zij times Vj, like this. And so we find that not only do we have a correspondence of expressions between this guy and this one, but we have a correspondence of this to this. So the same process of raising the index for our basis vector and lowering the index for the basis vector also works for the covariant and contravariant components, the scalar components of our vector. So we have an operation that lets us raise the index or lower the index. And so this is an extremely useful technique, and you're going to see it happen over and over again in things as we move forward. It gives us the ability to switch from covariant to contravariant factors anytime we want to, or vice versa. If you're working with covariant components, you don't like it, you want to work with contravariant components, this simple little expression will convert them so you can use the ones you want. Now, the vector can be expressed either this way or this way. So the covariant and contravariant components are equivalent. They're not the same, but they're equivalent. That means that they carry the same information about the vector, and each one is as useful as the other. So we can trade one for the other anytime we want it using these expressions, these two formulas for raising and lowering indexes. Maybe you can appreciate now why we refer to the metric tensor as the fundamental tensor, because it is something of a conversion factor that connects the covariant and contravariant components of vectors and the basis vectors. Okay, well what we see working here for components and basis vectors also works for tensors of higher rank. So let's take a look at that. Let me move up here a little bit. Suppose I have a second rank tensor, Tij, that looks like this, and I form a contraction now with our contravariant metric tensor, and I'll use the letter R this time, and contract with the I index. So what was originally a second rank tensor, twice covariant, now when I form this contraction, I is now a dummy index, so it's no longer a free index, but I've introduced the R index. Well, that converts the rank of the expression to a tensor that looks like this. It has R in the upper position, and it has J remaining in the lower position. Now here I put a dot in this position to show that we have raised the first of these two indexes into the R position. Well, now if I take this tensor, which is T R dot J, and I form another contraction, this time with S and J as the dummy index, I'm forming another contraction or an inner product, and this time what was a second rank tensor, once contravariant, once covariant, now it's going to become a tensor that is twice contravariant, like this. So I use the same idea of forming these contractions to raise the indexes, only I had to do it twice this time in order to get both indexes raised where they belong. Okay, now I could have done this in a single operation. I could have taken Tij, formed a contraction with Ri here, and another factor of Rsj here. So I have a double contraction. I've formed a dummy index with I and with J, and the S and R components will take the place as it moves up into the position of TRS. So the operation of raising the index works the same way. And you could see that in reverse it would work by lowering the indexes. Now let's be clear that I could have started with Tij and formed a contraction first of all with the S first. I could have done Sj, and that would have formed a tensor that looks like this. This time the dot is here with the S and the I because I'm raising the J index into this second position. Then I could have taken T dot S I and formed the contraction of Ri, and we get the same result as before. The order doesn't matter. I can do one first and the other second. Now, let's say a word about these placeholders, these dots I put in place. Now, we said a moment ago that covariant vector components and contravariant vector components are equivalent. They carry the same information. So we can represent the vector in one of two ways with these sets of components. Well, vector components are really first-rank tensors. Well, if we look at a second-rank tensor, we know that we can represent that with lower indexes as a covariant tensor, or upper indexes like this, or as a mixed tensor where we have I and J. But the point I'm trying to make here is there is a difference between I.J and .ij. Just because we have an index on top and bottom doesn't mean that these are the same thing. In fact, in general, these two will not be equal to each other. So the order in which you raise these, if we raise them both in the end, we'll get the correct result. But if you raise only one of them and you raise the other one in a different order, the matrix that you produce here is not necessarily going to be the same. So we use these dots as placeholders to distinguish between the two forms. Now to understand this better, let's do a more complex example. Suppose we have a sixth rank tensor that looks like this. IJK on top, RST on the bottom. Now for whatever reason we decide we want to lower the J index. Well, we need a factor, first of all, that's a covariant metric tensor term because we're lowering the index, and so we need a new letter, and then we'll contract on the J index like this. So we're going to drop the J index using this particular technique. Well, where does it go and what does it look like? Well, here's a convention that I use, and I think it's used by most authors, but not everyone. And it's this. We consider the upper indexes to lie to the left of the lower indexes. So the meaning of this expression really is this. mj, t, ijk with 3 dots as placeholders. And on the bottom, we start with 3 placeholders and have R, S, and T. Now, if we arrange it this way, we have no trouble in seeing that lowering the J index would result in a tensor that looks like this. I dot K with 3 dots, and then dot M dot R, S, T. You can see how nicely everything winds up in its own slot or its own position. And then because of the convention, because we understand that the lower indexes trail the upper indexes, we don't need any trailing dots on the top or any leading dots on the bottom. So the end result here is I dot K, and on the bottom it's just M dot R, S, T. Okay, now I mentioned this convention is very popular, widely used, but not by everyone. So be careful when you read other literature that you understand what the author uses. Sometimes they do it just the reverse, so make sure you understand the convention the author's using. All right, there's one very important exception here. We said earlier that Ti dot j is in general not equal to T dot I j in this form. And in general, that's true. But if our tensor Tij is a symmetric tensor, then these two forms will be equal. So if and only if the tensor is symmetric, we'll find that this statement is true. And because it's true, we are okay just representing either form as Tij without any dots. And I say all of this because most of the second-rank tensors we encounter will be symmetric tensors, so you'll see this form quite often. And just realize that there's no ambiguity here because raising the right index or the left index first will result in exactly the same matrix. All right, I got one more topic to cover now. Suppose I have this expression, R, I, and Ti combined as an inner product like this. Well, I'm going to replace the first factor with this, Z, I, M, R, M, with an upper index. I hope you see that this expression is the same as R with a lower index of I. I'm going to do the same thing with T. I'm going to replace it with this expression. And I hope you see that this factor is the same as T with an upper index of I. Okay, collect the terms a little bit. We have Z, I, M, Z, I, K, and we have RM and TK like this. Well, the combination of these two factors, a contraction of one of the indexes of the covariant and contravariant metric tensors, will result in a Kronecker delta, Km like this, Rm and Tk. The Kronecker delta will absorb, let's say, the M index, leaving us with Rk, Tk, and we can always rename the indexes of any dummy index. Leaves us with this result. RIT is equal to RIT. Now I call this the flip-flop because anytime we have a contraction like this, a dummy index, we can flip the positions of the dummy indices if we do both at the same time. So I can raise the index of R while I also lower the index of T, and this operation is always permissible. Don't need to go through this whole exercise. Anytime I see a dummy index, I can flip the two indices, one going up and the other going down, and the results will be exactly the same. Okay, I think that's quite a bit for one video, so let's go review what we've done. We first discovered that forming an inner product between the contravariant metric tensor and the covariant basis vector had the effect of raising the index and giving us the contravariant basis vector. And we see that the same thing happens when we use the contravariant metric tensor with a covariant vector component. It also has the effect of raising the lower index here to give us the contravariant vector components. We then discovered that the converse works as well. If we form an inner product using the covariant metric tensor with the contravariant basis vector, the effect will be to lower this index and give us the covariant basis vector. And the same thing happens with vector components. We can lower the index from a contravariant component to a covariant component like this. So with these tools, we can raise and lower the indexes anytime we need to. We then went on to look at the operation as it applies to higher ranked tensors. We started by looking at a second ranked tensor. We raised the I index first by forming this contraction, so the R index appears on the right-hand side. Now I have set these two forms equal to each other because of the convention we talked about. We said that the upper index is understood to be to the left of the lower index, so we don't need the leading dot here to understand that that's the meaning of this expression. On the other hand, if we started by raising the S index first, such as down here, we do need to retain the dot because if we didn't have the dot there, we would understand the S to be to the left of I, and it's not true. I is to the left of S in this relationship. Now I'll remind you here of our important exception. If T is in fact a symmetric tensor, then it would be okay to represent this result as T as I. And the reason is because this expression would result in exactly the same matrix as this expression. But that's only true if we have a symmetric second-rank tensor. Okay, in either case, if we start by raising I first, we can raise J next to get this. If we start with J first and then raise I, we get the same result. Or we can do both operations as one expression. By creating a double contraction like this, we raise both I and J at the same time. Then we went through a more complicated example in which we illustrated the fact that due to our convention, this form of the tensor actually means this. And because of it, it's very clear where the J index drops down into the second position on the bottom. And ultimately, because of the convention, we can drop the trailing dots on this side and the leading dot on the bottom, giving us the final result that's here. Now, in the recap, I've given you the inverse operation where we start with this tensor right here and show you an operation for raising the M index back into the second position. And we would do just the opposite. We would insert the trailing dots and the leading dot here, and that makes it easy to see that the M index goes up into this second slot, giving us this form. We can drop now the trailing dots and the leading dots and go back to the original form of the tensor back here. That also shows you that these operations are reciprocals of each other. They're inverses. One produces this form, and doing this takes us back to the original form that we had. All right, and the last thing we did was to show that we can do a flip-flop on dummy indexes, and this is the example we used in doing the derivation, but it works anytime you have dummy indexes. For example, in this illustration, I flipped both I and J so that the I and J appear on top here instead of bottom, and these two drop to the bottom like this. Don't need to do any calculation or derivation. I can just flip-flop these dummy indexes anytime I feel like it. All right, with that, I think you have a pretty clear understanding of what it means to raise and lower indexes.